In this lesson, we're going to introduce more formally Ampere's law, which, as we said, was our integral, closed integral, line integral, b dot ds equals mu naught I. And in this lesson, we are going to show that specifically it is the I enclosed. So we saw this before with Gauss's law. Q net enclosed over epsilon naught. If you remember, Gauss's law was our integral equality from E dot dA was equal to Q enclosed over epsilon naught. Now we're going to show on this page of notes why it is that the currents that are not enclosed, and we'll talk more about what we mean by not enclosed in a second, do not contribute to the integral, just like charge outside of a Gaussian surface did not contribute to that integral. Well, the first things first, our closed path we are now going to refer to as Amperian loops. So just like we had Gaussian surfaces, we have Amperian loops. By convention, and we'll see more about that why in a second, they are going to run counterclockwise. So here we just have a blobby loop, and our direction is counterclockwise, and the ds in the integral is a differential part of that path, that Amperian loop. Okay, please make sure you get that into your notes. Well, what we are going to focus on this page of notes largely is what is the angle theta doing in our dot product. So our B field is the B field from the wires, and we're going to assume these are all long straight wires, so that in general our B field for the long straight wire is mu naught I on 2 pi r, as we have already seen earlier from our Biot-Savart law derivation of the finite wire, and then extending it into an infinite wire. Well, let's take a look at what is going on with this dot product relative to, let's take a look first at the I enclosed and see what is going on with those. Well, please make sure you draw in the B field arrows here, so you can either use your right hand thumb pointing in the direction of the current I1 and curling your fingers to get B1, but let's do an actual IDL cross R hat for this one point in space here, right? So if we do IDL cross R hat, thumb in the right hand thumb in the direction of B1, please confirm that you get that direction for B1 when you do your IDL coming out of the paper, perpendicularly out of the page, right hand in that direction, making a fist towards you, B1 in that direction. The ds is always tangent to the path. So ds is always tangent. Instantaneous vectors are always tangent to the vector path shown. So the ds will always be tangent. And notice, and please get this into your notes, notice that for any of the B1s and the ds's around the entire loop, since B1 is a counterclockwise, right? A counterclockwise direction, and the loop is counterclockwise, you will always get theta in that cosine of theta between 0 and 90 degrees, and will always be positively valued. Now, maybe you can guess what will happen if the current is running into the paper. If the current goes into the paper, then again, please confirm, make your right hand thumb stick into the paper, curl your fingers to get the B field direction. So do the IDL cross R hat to get the tangent B2 over here, and then the tangent ds here, and I have those drawn in for you. And the angle theta, since the B field direction is going to go clockwise, whoops, let me go with my blue, clockwise, and the ds direction runs counterclockwise, that you will always get 90 to 180, so the dot product in our integral up here is always going to give us negative. So because of that, we are going to label those i's as positive if they come out of the paper and negative if they go into the paper to get the I net enclosed. Right? And so our convention works, and we are always going to use counterclockwise direction for our Amperian loops. And to finish up this page of notes, let's just see why it is that any of the currents that are outside of the loop will end up not contributing to the integral, and please make sure you get this down into your notes. If we look at a current that is outside of the integral, the B field, since the I is coming out of the paper, the B field is going to run, let me get black in here real quick. The B field is going to run counterclockwise at all points in space. Since ds runs counterclockwise, we will get the situation where for portions of the loop, right, that correspond to motion opposed to the B3, we get theta between 90 and 180. But over here on this half of the loop, we get B field that runs in the same direction as the ds. And since the loop is a loop, you will always get half the loop going in the direction of B1 and half the loop going against the direction of, the B3 in this case, the B3. So the current 3 and the B3, right, that makes the B3. When we do B3.ds, we'll always have those negatives and those positives cancel each other out, always, regardless of the shape. Since it is a closed path, that will be the case, and currents outside of the loop do not contribute to the integral, do not contribute to Ampere's law. So hopefully this demonstrates why we won't be using currents outside of the loop. So that's what we're going to be doing from now on. We'll kind of get a summary of what we're doing with Ampere's law on our next page of notes and start some problem solving.